what we're going to be learning today. So we've talked about logic these past couple of meetings. We've talked about translating logical statements into symbols that we use. But we haven't really talked about assessing their truth value just yet. Well, that's what a truth table is going to be all about here. So truth tables, we're going to see what the truth table is for the negation, conjunction, and disjunction. So we start with a basic truth table. What a truth table does is it lists out all the possible truth values for a given statement. And then you can start adding layers onto it and see what the truth value will be for those layers. So the most basic truth table we can look at is the negation. If you're starting with a statement P can either be true or it can be false. So in this first column here, we list out all the possible combinations. There's only two for a single statement, true or false. And then not P, when P is true, not P must be false. When P starts off as false, not P must be true. It's a pretty simple sentiment, but it's also a very important one. So let's look at an example. Let's say I'm going to write something down and we don't necessarily know if it was true or false. Your instructor was born in 1990. Instructor me, Josh, I was born in 1990. Is that true or false? Well, consider the following. P is the statement, your instructor was born in 1990. Let's make a truth table out of that. We're going to start off with the statement P. Now, like we said, P is either going to be true or it's going to be false. So that's all we do here in this first column. We just declare that it's possible truth values, and it can only be one or the other. Now consider for the moment the statement not P. Not P, well, if P is the statement, your instructor was born in 1990, what is not P going to be? Very good. Your instructor was not born in 1990. Your instructor was born in any other year other than 1990. Well, on the truth table, let's look at not P. If it's the case, not P. If it's the case that P is true, if your instructor truly was born in 1990, what would the truth value be for not P? If I was born in 1990, then the statement I was not born in 1990 must be what? False. Exactly. Whenever this statement is true, its negation is false because they're opposites. However, let's say that the statement I was born in 1990 is actually false. What would not P have to be? True, exactly. It takes the opposite sentiment. So all we're doing with the truth table is we are listing out, using logic, the truth values of different compound statements that we're making. And so just anytime you have the not of something, you just literally flip-flop all its truth values. It's really simple, straightforward. Now the conjunction is a lot more interesting. The conjunction is a lot more interesting. The first thing we'll note is that now we have to be able to conjunct two statements. So we need both a P and a Q truth table. We need both a P and a Q truth table here. Thus, our very first column, it needs to be just our basic statements and all the possible truth value combinations between them. We need to know, hey, whenever the statement P is true and the statement Q is true, what does that mean about the conjunction, the and of them? Whenever P is true and Q is false, what does that mean about the conjunction? When P is false, Q is true, what does that mean about the conjunction? When they're both false, what does that mean about the conjunction? That's all this is. Each row is a different combination of truth values for your starting statements. Now, you could memorize this basic table for the conjunction. You could do that. I think that's a little bit of a waste of time. It's a wasted endeavor. Let's look at it a different way. Let's say we'll use our example that we started using last week. Let's say you're going to a bar, and this bar requires you to be at least 21 to get in, like most bars do. Not every bar does, but most do. Let's say they also have a band playing, and so they're going to charge you a cover. You literally have to pay them an admission fee, if you will, to even get in the bar, on top of being 21 years old. So let's say the statement P is you are at least 21 years old. Let's say the statement Q is you are willing to pay a $10 cover to get into the bar. Let's say those are our two basic statements. And let's say we're trying to get in Bar Exclusivo, which requires both rules. So let's look at the four possibilities here. Give me a second to make this chart. Let's look at the four primary possibilities. Move that a little bit. Give me a sec. It's fun to make these charts by hand. The nice thing is, for the most part on your online homework, the charts are already made. You have to fill them out correctly, but you don't have to try and awkwardly draw a bunch of stuff. Okay, so here's what we're going to do. We're going to put the initial statements P, Q. This third column here, this is going to represent whether or not you are allowed in Bar Exclusivo. It's going to be the conjunction P and Q. If you get a true out of this, you get to go into the bar. If you get a false on this column, you do not get to go into the bar. So let's see. We could be, it could be the case that a person is both at least 21 years old and willing to pay a $10 cover. That's literally what this means. P and Q means at least 21 and willing to pay a cover. They're both true. Will Bar Exclusivo let you in? Yes, they will. You must check both of their boxes. So it's true, you're allowed to go into the bar. So this would be, this line right here This represents someone who is at least 21 and also has and is willing to pay the $10 cover. I'll even put that here. And willing to pay a $10 cover. That's what the first line represents here. What's that? Yeah, exactly. Because P is the statement you're at least 21 years old, and we're saying that's true here. Thus, you're at least 21 in this particular example. Which is why if we look at some of the next lines, we'll deal with that situation. So now let's look at the situation for someone who is at least 21, but they're not willing to pay the $10 cover. Either they don't have it or they just don't feel like paying to go into a bar where they're about to pay for a bunch of drinks. They think that's stupid. So you're at least 21, you're not going to pay the money to get in. Is bar exclusivo going to let you in? No. So you're going to get a false there. Bar exclusivo says, okay, bye-bye. That's it. Thus, we put a false there. This is anyone at least 21 who's over 21 years old, 21 or up, but not willing to pay the $10 cover for whatever reason. Not willing, or they don't have the money. That's what this line represents. Next up, let's say that P is false, meaning that whoever this person is, they're not at least 21. They could be 18, 19, 20. I guess they could be 17, 16, trying to pass off as someone older. It's not going to work. Let's say that it's not going to happen. Let's say they are willing to pay the $10 to get in. They have it, and they're willing to part with it. Is bar exclusivo going to let them in? Not on your life. Just you must be at least 21 to get in. It requires both rules. So false, you're not getting into the bar. And so what is this? This is anyone under 21, strictly less than 21, even though they're willing to pay the cover. They're not getting in. Finally, the last line, you're going to have someone who is both under 21 and they're not willing to pay the cover. Is that person getting in the bar? Definitely not. And so this is anyone under 21 and unwilling to pay the cover, or unable, whatever. And so there you go. So the conjunction, the and operator is exclusive. If I conjunct two statements, they must both be true for the conjunction to be true. That's how it works. You have to be coming to the table with two truths. And then when I conjunct them, that's the only way you're going to get a true statement out of them. If either statement or if both statements are false, the conjunction is false. So the conjunction is the harder one to get a true statement out of. But that makes sense. If I come up to you and I shake your hand and say, hello, my name's Josh, I'm a billionaire, and I'm a super genius. Well, if it just so happens that I'm a billionaire, but I'm not a super genius, was my previous statement true? No. One part of it might have been true, but because I used the word and, both things had to be true for the entire statement to be true. So now you can imagine, the only way for that statement to be true is if I am both a billionaire and I'm also a super genius. I've got to have both those things. If I have only one of them, if I have neither of them, that whole statement is not true. That statement's probably only true for a handful of people around the world. I bet Elon Musk, most people would say, super genius and a billionaire. Jeff Bezos, I don't even know if you would say he's a super genius. He might just be really good at business and marketing, but Musk is. What's that? Maybe, yeah, yeah, yeah. So there's a couple examples out there, yeah. Obviously, it would be cool to be a billionaire and a super genius, but that's just not going to be true for everybody. That's just how life is. So the conjunction is said to be kind of exclusive. It's harder to get a true statement out of it. The disjunction, the or statement, is a little bit more lax. It's a little more relaxed. The or statement just says, hey, at least one of the statements coming in here has to be true for the or statement between them to be true. The only time the or statement will be false is if both of the statements bringing it together are false. That's the only way. So if I walked up to you and I said, hi, my name is Josh. I'm a billionaire or I'm a super genius. Now, someone's probably not going to say that in passing, so this is just kind of a silly idea, but let's play along with it. If I walk up to you and I am a super genius or a billionaire, is what I tell you. What if the truth is I really am a super genius, but I'm not a billionaire? Was my statement still true? Yeah. Hey, I'm a super genius or I'm a billionaire. Only at least one of them has to be true. If I shake your hand and say, hi, I'm a super genius or I'm a billionaire, and it turns out I'm only a billionaire, I'm just a billionaire, is that statement going to be true? If I say I'm a super genius or I'm a billionaire, but I'm only a billionaire, yes, that statement's going to be true. Let's see what's this thing has new problems every day. Okay, sorry about that. Now, in the case where I actually truly am, I'm a super genius, I'm also a billionaire. If that were the case, and I come up and say, hi, I'm Josh, I'm a super genius or I'm a billionaire. That statement is still true because remember in logic, the word or means and/or. So you can have both of them be true and the or statement is still true. It's not the either or that we normally use the word or to mean. So let's look at the disjunction. The disjunction P or Q is true as long as at least one of the statements coming into it is true, which is the case here, the case here, the case here, but it's not the case here. Let's go back to our little fun example. In our fun example, we actually don't have to change this first column at all, because all this first column does is it gathers all possible combinations of being true or false between the two starting statements. So if you have statements P and Q, this is first column here, it's going to be called your declaration column. You're just declaring all the possible outcomes. Now, bar inclusivo only requires one of the two rules above for you to be able to get in. Bar inclusivo, we're going to say the or now, not the and, we're using the or. The rules are still going to be you're at least 21 or you're willing to pay a $10 cover. Why might a bar do this? Well, there are some bars who allow 18, 19, and 20-year-olds in. You're still an adult. The only other stipulation is, well, yeah, never mind. They're still going to require you to be at least 18. So just keep that in mind. So let's look at P or Q. In this case, this first case here, both P and Q are true. That is, this is a person who is at least 21 and they're willing to pay a $10 cover. Is the bar going to let them in? Absolutely. A bar will do this when they'll let you, like a 19-year-old in, which they legally might be allowed to, depending on the city. But if you're 19, they can't sell alcohol to you, can they? No, not legally. So they might let a 19-year-old in, and then they'll say, but you got to pay $10 so we can get something out of you. We want to be able to get something out of you because you're not going to be in there buying alcohol. You might get a Dr. Pepper or like some chips and queso, but you're not going to be spending the real money, which is on drinks, on alcohol. So they'll let you in if you're at least 21 in this case, and if you're willing to pay a $10 cover, sure, they'll definitely let you in. So this is for anyone who's at least 21 and willing to pay a $10 cover, they'll let you in. This is anyone who is at least 21, they're not willing to pay the $10 cover though to get in the door. Now at Bar Exclusivo, that was a problem. At Bar Inclusivo, is that a problem? You're at least 21, you're not going to give them $10 to get in. Will they let you in? Yes, Bar Inclusivo just says you got to have one, you got to be one of these two things. Because if you're at least 21, they're hoping you're going to come in and spend a bunch of money on alcohol. So this, in this case, they will let you in. Does that make sense? You must be one or the other. You must be at least 21 or willing to pay a $10 cover. In this line, this is for a person who is at least 21. They're not willing to pay the $10 cover. They're still going to get in. The bar will let them in. In this case here, P is false, Q is true. So we look along the row. This is someone who's not at least 21, but let's assume they're still at least 18. Let's say this is a 19-year-old, but they're willing to pay $10 to get into the door. Will this bar let them in? Yes, because again, we're following just one of the two rules, but that's enough to get in. Finally, this last line, this is someone who's under 21 and they're not willing to pay $10 to get in. Will the bar let them in? No. That's the only time. So the disjunction, the or, is only false when both statements are false. Otherwise, it's true if at least one of the statements is true. And that's why I call it more inclusive. It's a lot easier to pass this test than it was at the other bar. Any questions on that? Does it make sense? Is it clicking? Is it vibing? Very good. Again, you're always free to stop me if you have a question. So now we can play with all kinds of truth statements. We can do this. Let's say P and Q represents the following statements. P is the statement 10 is greater than 4. Q is the statement 3 is less than 5. And let's hide the answers. So these are our two statements. 10 is greater than 4. 3 is less than 5. Well, real quick, let's ask ourselves, hey, is 10 greater than 4? Yeah. So P is an inherently true statement. Right off the bat, we can see that. The next statement, Q, 3 is less than 5. Is that a true statement? Certainly. 3 is certainly less than 5. So it just so happens that both of these statements are true. That's not always going to be the case. Sometimes you won't even know if they're true or false. You won't even know. You have to do more research. So now we need to look at this, the statement P and Q. Well, I'm doing a conjunction, that's the and. I'm taking a true statement, conjuncting it with another true statement. And what will that end up being? True. See, this is the statement, P and Q. This is the statement in English. 10 is greater than 4, and 3 is less than 5. That's what P and Q translates to. Is that a true statement? Bet your bottom dollar. 10 is greater than 4, yeah, and 3 is less than 5. Yeah, those are both true statements. So when I bring them together using the word and, I'm creating a true statement out of that. Now down here, we've got not P and Q. This is equal to the statement. Well, it's not P, so it's got to be the opposite. So 10 is not greater than 4, and 3 is less than 5. Now this second statement is still correct, but we've hitched our horse to a statement that is now false. 10 is not greater than 4. That's a false statement, isn't it? So now I'm taking a false statement, conjuncting it with a true statement. So ultimately, this looks like false and true, which is going to be false. If you go back to your conjunction table, that's a false and a true statement. False and true is going to yield a false statement. So just some good ones to know. Let's look at it some more. The same two starting statements. P is the statement 10 is greater than 4. Q is the statement 3 is less than 5. And now we got to determine if the statement P or not Q is true. Well, this is equal to the statement P, 10 is greater than 4. Or, well, it's not Q, or 3 is not less than 5. That's what that translates to. What's that? True? I would agree. Because the P is a true statement. P is a true statement. I'm doing the or. Well, not Q, since Q is true, not Q must be false. But since I'm doing the or, just at least one of them has to be true, which is the case here. And so it's true, like you said. Very good. Down here, not P or not Q. Well, P and Q both started off as true, but not P is then going to have to be false, isn't it? And not Q also has to be false. So if we do the false statement or a false statement, what do we end up with? False, exactly. It's the only case where the or statement comes out false. Now here's the cool thing. Here's the cool thing. Give me a second. let's construct a truth table for not P or not Q. Here's what we're going to do. We're going to build it piece by piece. No matter what, we have to start off by declaring all possible truth combinations of P and Q. They're both true. P is true, Q is false. P is false, Q is true. P is false, Q is false. You're going to be seeing this first column here a lot. And now the ultimate statement we want to create is not P or not Q. So I need to know what not P is going to be. I'm going to do it piece by piece, operation by operation. And so this is going to be an interesting challenge. Give me 1 second. I'm going to need a not P column. I'll also need a not Q column. And then I'll need a column for the entire table. So let's see. I needed a not P column. I'll also need a not Q column. Finally, I'll need a column for the whole shebang, not P or not Q. And now we can just fill it out piece by piece. Here's the not P column. Do we even need to look at the Q column at the moment? No, we just need to take our P column and do the not of it, which is to say, take the opposite. So in this first row, P is true, thus not P is false. Here, once again, P is true, thus not P is false. Here, though, P is false, so not P is true. Again, P is false, so not P is true. Now I need to fill out the not Q column. So I need to take the Q column that we started with and take the opposite. Q is true, so not Q is false. Here Q is false, so not Q is true. Here Q is true, so not Q is false. Here Q is false, so not Q is true. Now I can fill out this table. I'm doing the disjunction, I'm doing the or between this column and this column. So I'm really completely focusing in on these columns here, and I'm going to do the or between them. So I'm doing a false or a false statement. What does that give you? False, exactly. A false or a false statement is false. A false or a true statement is what? True. Because when you're doing the or, you just need at least one of the two statements to be true. Then the whole thing is true. Here I'm doing a true statement or a false statement, which will give me true. Here I'm doing a true statement or a true statement, which will give me still true. Yep. So this is the truth table for not P or not Q. We literally, for every possible combination of P and Q, we can go look on the table and find the appropriate truth value for the statement not P or not Q. So going back to the PowerPoint, we have the statements P, 10 is greater than 4. Now we actually have real values for P and Q. Q is the statement 3 is greater than 5. We said that P was true, the original P. Q, the original Q, was also true. That was the specific value for this specific example we're giving. In this truth table is general, meaning I can make any truth value for P and Q and figure out what the truth value for this whole statement is. Because from the PowerPoint, I'm starting with a statement P that's true and a statement Q that's true. We're going to focus in on the very first row. That's going to be the only thing we care about for this specific example. And then we see that its truth value is false. The ultimate truth value we're looking for is false. And so that's our answer here. That's the usefulness of a truth table. It gives us the truth values for every possible combination that exists under the sun. Yeah, oppositing is real nice. It's real straightforward. True is false, false is true. Now, if I went into this and I just changed it slightly, I just changed my statements P and Q, ignore now all this business down here, except for here. Now, what is the truth statement of not P or not Q? What is its truth value? Well, now we've got a statement P that's true. The original statement is true, but is statement Q true? No. Statement Q is now false because of the little tweak I made. So I've got a true P, a false Q. So now when I go look at my truth table, I'm no longer looking at this row because this row has both P and Q being true. Now I want P true and Q false. That's this row. And now I can go all the way to my thing at the end here. And now this is the truth value of the statement, not P or not Q. So it's kind of like this thing here is a math equation that has variables X and Y. And what we've done is we've thought of all possible solutions that could exist. But now once we know what X and Y actually are and we plug in values for them, now we can know what this thing actually truly comes out to be. That's kind of what we're doing here. So that's why it's cool. So it's like having a math equation, keeping it in general in terms of your variables, but then finally you can start plugging in variable values. So let's do some more. Let's construct a truth table for the statement not, and then in parentheses, P and Q. Let's do that ourselves. It's more fun that way. So let's vacate some of this. Give me a moment. I don't want to destroy the whole thing. So now we're going to construct a truth table for not P and Q. All right, well, the good news is, oops, that's right. The good news is I can alter this fairly simply. We only see two total computations here. We have to do a not, but we also have to do an and. Now the P and Q is in parentheses, meaning we let P and Q be its own thing. We do the P and Q first, then we take the not of it. In other words, the inside of our truth table, we're going to need a column for P and Q. Then your last column is usually going to be the final thing, the last thing. We'll have a column for not P and Q, which will just be the opposite of whatever we get in this column. So let's do it one step at a time. We've got P and Q. We're taking a true statement. We are conjuncting it. We are doing the and with another true statement. What will that give you? True, exactly. The and statement requires two truths to be true. You're doing a true statement and a false statement. What will that give you? False. You're doing a false statement and a true statement. That'll give you false. You're doing a false statement and a false statement. That'll give you definitely false. And so now we've done P and Q. All we got to do is the opposite of it. We look at the P and Q column and we just take the opposite of it. So true. So we literally can ignore this starting column now. We've got everything we need right here. The opposite of true is false. The opposite of false is, the opposite of false is, the opposite of false is true again. Yep. And so that's our truth table for the statement, not P and Q, where P and Q is in parentheses. That's all we needed to do with this one. Let's say our statements, let's move it over a little bit. Now let's look at a specific example. Let's say P is the statement. Shakespeare was born in 1999. Say Q is the statement. Josh is the smartest instructor in the world. Remember, I'm Josh, the person speaking right now. Now let's determine the truth value of the statement, not P and Q, if you will, which translates to, it is not the case that Shakespeare was born in 1999 and Josh is the smartest instructor in the world. Well, wait a minute. We already have our not P and Q column all fleshed out. All we got to do is determine which combination of truth values illustrates this situation. So in other words, we go right over here, we look at P and Q separately, and we determine independently their truth value. The first one, Shakespeare was born in 1999. Is that true or false? Absolutely false. Some person named Shakespeare might have been born then, but it's pretty clear I'm talking about the bard, William Shakespeare. Q, Josh is the smartest instructor in the world. This is a trap. Is that true or false? Absolutely true. Thank you. You did not fall into the trap. So, but you know, even if Q was a statement that can clearly be verified as true or false, which, I mean, this is probably just opinion or silly. I mean, even if you used IQ, IQ is still considered an opinion, whether that truly measures intelligence. But let's just assume you start with a false P and a true Q. That means you must be talking about this row here. False P, true Q. You don't care about this guy at all. This is just an intermediary to get you to the last statement. And so the truth value of the statement not P and Q, it is, in fact, true based on these inputs. Can you start to see why this is, well, this is actually truly mathematics? It's because think of a formula. Think of the quadratic formula you used back in algebra. Negative b plus or minus the square root of b squared minus 4ac all over 2a. How many of you kind of remember that thing? Determining the roots of a quadratic equation. If you know what a, b, and c are, those are the coefficients. If you know they're going to be numbers that you plug into that formula. So all a formula is in math is something that lets you plug values in for the variables, and then whatever it spits out is the answer. That's the entire process of mathematics. What we're doing here is the same thing. We may not know what, they may not be numbers that we're talking about. Instead, our formulas just look like little logical symbols. And then once you decide on values for your initial statements, false or true, you plug them into a formula and then you get an answer pop out of that formula. Now here, the inputs and the outputs are simple. They either got to be true or false. They can't be numbers like 9 and 4,000 and negative 27. So there's a much more limited scope for what you can put in or out or take out. But it's still mathematics all the same. It's very similar to mathematics. In fact, these are what we're actually doing here is what sets up the foundations for math that you've actually learned before now. So really, we should be teaching second and third graders when they're just learning math, we should be teaching them this kind of stuff. And I won't say it's easy, but I think if you put the time in, it's something that can be conquered and understood. I think it could be understood by just about any age group if you made it simple enough. So this is kind of the math. This is actually what math really is. It's logic. That's all it is. Math could almost just be seen as quantificational logic. Logic with some numbers thrown in. That's really a lot of what math is, at least the math we're going to experience in this course. But I promise you, this is more math than what you've seen before, even though it doesn't look like math. It's a weird little paradox almost. Let's see, we go till 11:45. Okay. I gotta be careful because I'm so passionate about this stuff. You remember the other day I went over, I literally didn't even realize it. I just kind of got carried away. So we just did that one. We don't have to look at that. Let's construct a truth table for this thing. Oh, that's nice. They filled it in for us. Nope, that's not gonna work. Let's do it ourselves though, because this is good practice. Yeah, it's gonna kill my lines a little bit. That's okay. Unless I do this. Yeah, let's just do this. Stand by. What we're going to do is we're going to fill in this truth table completely on our own. We're going to blaze our own trail. And you're going to see that it's all perfectly logical, makes sense. Okay, so the truth table that we want to construct is for the statement, in parentheses, not P or Q, and the statement not Q. Well, let's see. We've got 4 total computations that are going down. We have a not, we have an or, we have an and, we have one more, not. There's 4 total computations, if you will, if that's what you want to call it, kind of like add, subtract, multiply, divide. So other than the initial starting column, we need 4 more columns, 1 for each of the computations. You need a column for not P because not P is one of the initial things that's happening. Once you have not P, you can actually do not P or Q next. Thus, that's the next column that you could do here. Now, the next computation is an and, but I can't do it yet until I know what not Q is because that not has to go straight to the Q first. So I'm going to do not Q as my next computation. Then finally, I can do the whole thing here at last in the column. So let's start off. We're just going to do it. PQ, remember, the very first column, you're just declaring all the possible combinations of truth values. PQ got to be both true. You could have the case that P is true, Q is false. You could have the case that P is false, but Q is true. And then you could have the case that they're both false. Is there any other truth value combination here? No. They can only be true or false. There's no maybes or possiblies. They're either true or false. These are all the combinations. There's nothing else you could scrounge up. Do you absolutely have to do it in this order? If you put false, false first, then false, true, then true, true, then true, false, technically you're not wrong. As long as the rest of your table follows logically and you've done it correctly, you're actually not wrong. But we're going to go ahead and say this order is preferred, frankly, because it's easier to look at your truth table and decide if you have the right answer. If everything's in the correct order, then all of this will be in the same order for everybody. So this is the preferred order for your initial column, your declaration column. And now let's do it. The first column we have to compute is not P. All we do is take the P column and switch it completely. So true, true, false, false becomes, yeah, false, false, true, true. Now here's where things can get a little wonky. We have to do not P or Q. So let me highlight. This is not P or Q. This is the one we're focusing in on. So we are looking only at these two columns to construct it. The not P column, we are doing the disjunction with the Q column. So a false or a true statement is what? True. Exactly. A false or a false statement is what? The only time that the or is false. A true or a true statement is true. And then the last one will be true as well, because we're doing a true or a false statement. And now I can erase the blue. That was just to help us in that moment. Now we need to do the not Q column. What is the only column we care about that's going to help us with this? The original Q column. Yeah. That is the only thing I care about in this particular case. So I'm just going to take the Q column and do the exact opposite of it. So the Q column is true, false, true, false. Perfect. Exactly. So the not Q column is false, true, false, true. So it's kind of cool how these charts play out, I think. Finally, let's do orange. Finally, we're ready to do the whole thing. We're doing the entire computation, the main one. You understand, though, why we had to do this piece by piece. It's like a big order of operations problem when you have numbers. You got to do it one piece at a time, one computation at a time. So I've got to do the not P or Q column, which is this one, and I'm anding it with the not Q column. So these are the only two columns I care about now. Everything else was just to help me build up to this point. Then keep in mind what your operation is. Your operation is the and that you're doing here between them. You've already done all the other operations. And then you are anding this column with this column. The only way you're going to get a true out of this is if what? If both pieces that are going into it are true themselves. In other words, you got to have two trues here between the two columns we're looking at. That's the only way you're going to get a true here. So I'm doing the and with a true statement and a false statement, which will give me a false statement. Because the and is very exclusive. You got to be two trues to get a true here. I'm doing a false and a true statement, which is false. I'm doing a true and a false statement, which is false. But finally, the last one will be true, exactly, because I composed it of two true statements. It's the only way you're going to get the truth out of that. So the process was, we look at how many unique statements there are. There are statements P and Q. So there's really only two unique statements, and then just combinations of operations between those. Do you see an R statement? No, not there. Do you see an S or any other letter? No, not there. Thus, your first column here, the combinations were pretty simple. There was only 4 combinations. Well, when you throw the R into it, suddenly you get 8 combinations. This would be if you threw a third, you have a P, Q, but you also have the R column, a third statement thrown into the mix. It's going to kind of complicate everything. It's going to double the number of rows you're going to have. Why? How many of you want to see a cute little math trick? Little math trick? How many rows will your truth table need? Well, if you only have one statement, P, the number of rows are the number of combinations of truth values for your initial statements. You only have one statement. That statement can be either what? True or. So there's only two possible rows that you'll even need if you only have one statement. So if you just have one statement P, there's only going to be two possibilities. But now, if you have two statements P and Q, you have P, and then you have Q. P can be true or false, so there's two possibilities just for P, but how many possibilities are there for Q? Also two, completely independently. And we will learn in chapter 11 of this course, which is still several weeks away, we will learn something called the multiplication rule for counting. You would actually multiply these, and 2 times 2 would be 4. So if you had two initial statements, P and Q, you're going to need 4 total rows in your truth table, which is exactly what we have whenever we have two statements. You have P and Q, you have 1, 2, 3, 4 rows to your truth table. Now, if you have 3 statements, P, Q, and R. Now you've got P, but you've also, independently of that, you have Q, because the truth of P has no effect on whether Q is true or not. So you got to independently evaluate Q. And then you also have R. Now there's 2 things, P and Q. P could be by itself, true or false. Q can be true or false. R could also be true or false. So you're actually multiplying, and 2 times 2 times 2 is 8. So if you start off with 3 statements, P, Q, and R, you're going to need 8 rows. You're going to need 8 rows now in your truth table, which is exactly what this is. If you count, you're going to see that there's 8 rows to this truth table. And this is just the first column of the truth table to get your declarations out. How many rows would you need if you had 4 statements? You threw an S in there as well. Well, what's 8 times 2? 16. You got to double up the number of rows you needed previously. So if I threw an S in there, suddenly I'd need 16 rows. If I threw a PQRS, if I threw a T in there, I'd need 32 rows to my truth table. The good news is, for our purposes, we're going to stop at P, Q, and R and just need 8 rows to the truth table. And we're going to see this is already going to create a pretty gargantuan, huge truth table. And so we won't go beyond that. So that's a good introduction to the idea. The next stuff is going to start getting a little bit more complex. So we'll save it for next time. Let me take attendance real quick. Don't go anywhere just yet.